In this video, we are going to continue to discuss the third part on topic 2.4. Before this video, we have already mentioned the limit of sin theta over theta and how to prove it, and then use it to explain how to answer the questions of example 5.5a and 5b. So in this lecture, we are going to discuss another concepts called the concepts of limit when x is tending towards not a point on the x-axis, but x tends to positive or negative infinity. So this is a different type of limit where the limit is taken when x is approaching infinity instead of approaching a fixed point of x naught on the x-axis. So before we go into the precise definitions of the limit as x tends towards positive or negative infinity, we would like to look at figure 2.31, which is a graph of y equals to 1 over x. We have seen this graph many times since our secondary school. So here you can see that if you take a point on the graph of 1 over x and you let the values of x goes towards very large value, then the values of the function will tend towards the values of y equals to 0. So in this case, it is understood that the limit of the function is going to be 0 as x approaches positive infinity. If x is approaching minus infinity from the right, then so is the functions is also going to approach a value of 0 when x is going to negative infinity. So here the limit of the function for 1 over x is said to be 0. The precise definitions of the limit when x approaches positive or negative infinity can be referred to the definition as listed on the screen. So to understand the precise definitions as x approaches positive infinity for a function, you could understand this definition better if you understands how the definition of an function at an internal point is defined. So let me just make another repeated revisions for functions that has an internal point, right? So in order to prove the limit of a function fx is equals to the values of the limit of the function is L when x approaches x naught, is to form a sandwich of L plus epsilon, L minus epsilon, and the functions at any arbitrary point on the x-axis is always sandwiched within L plus epsilon and L minus epsilon for x that falls within an open interval of x naught plus delta, x naught plus delta, and x naught minus delta. So I have to write off this as n minus. So for any arbitrary values of epsilon, you always can find an delta interval that guarantees that values of the function always sandwich within the L plus minus and L plus epsilon and L minus epsilon sandwich. So here you requires the existence of the delta interval So here delta interval is expressed in terms of the epsilon. Whereas in the case of the limit of a function when x tends towards plus or minus infinity. So maybe I just look at the case for x goes to positive infinity. If the limit exists and say if it equals to L, so what it means is that we have to prove the existence of an open interval for the function of fx on any point of x such that the values of fx is always sandwiched between L plus epsilon, L minus epsilon. Here this is a line of L. So we need to prove the existence of an intervals in x where the functions is always sandwiched within this region for an open interval of a different kind, where in this case we have to show that there exists an open interval in the x space where the x that lies within this open interval can always guarantee these statements to be true. So in the case of an internal point, the open intervals is sort of like an limited region in the x space that is constrained to just lie in the delta interval. Here, the sort of like delta interval corresponds to the case of an function that has a limit when x tends towards infinity, have to be such that the existence of the delta is specified as in the form of x larger than some number m. So you have to prove that as long as there is a number of m such that the values of m that is lying between the values of m to positive infinity, then the conditions of fx minus L less than epsilon is always guaranteed. So in this case, you have to prove the existence of a number m, whereas in the case of an open interval, you have to prove the existence of a number delta, where in this case, the delta of the values of delta that specify the boundary of the delta interval has to be tied to the values of epsilon. In this case, you have to specify a values of m upon which when say you have a values of m somewhere here, you have to prove there is a values of m somewhere here that as long as the values of x is lying in a region larger than m from the values of m up to infinity, m is not included, then the conditions of fx minus L less than epsilon is fulfilled. And these values of m plays a role of the values of delta. Here, in the case of the internal intervals, delta is expressed as some numbers of epsilon. Here, you also have to express m as a function of epsilon. Okay, so the proof of the limit of a functions that has a limit when x tends towards infinity amounts to proving the existence of an number m where the x that lies in these open intervals starting from m to infinity will always guarantee the condition. So that is basically the idea of the precise definitions for the limit of x when x approaches to infinity. This is a very simple example of 1 over x. So here the values of L, which is the limit, is L equals to 0. and you form a sandwich of 0 plus epsilon and 0 minus epsilon. So you can show here that as long as the values of given any epsilon value, as long as the x is lying between m to infinity, basically the regions that is shaded in green, as long as x is lying within this region where values of m is 1 over epsilon, then you would be sure that for all values of x that lies in this region, the fx minus the L is always less than epsilon, where the L here is 0. Okay, so this is a statement that describes the green color region, and this is always correct when x is larger than m, where m is chosen to be 1 over epsilon. Okay, so in the case of the internal limit where x is tending towards x naught from both left and right, the delta interval is written in this form. Whereas in the case of an infinite limit, you don't have delta, but you have m. So here you type delta in terms of epsilon. Here you type the values of m to be to epsilon as well. But the way how you specify the interval is slightly different. In the case of an internal intervals, the delta intervals is limited to some finite regions, whereas for the case of proving the function that has a limit when x tends toward positive infinity is to show that there exists a values of m where as long as x is lying larger than m, then the conditions of this is fulfilled. So here the open intervals for proving this case of x tends toward positive infinity is slightly different as in this case where the open intervals is an infinite sort of like infinite set. Well, it's a set that begins from m to infinity. That is in contrast to the case of an open intervals of delta. So this is a simple example that shows you that how to prove the limit of y equals to 1 over x when x tends towards positive infinity. The same argument can also apply to the other side where x tends towards minus infinity. You also have to just prove that if you want to prove a function that has a limit when x tends towards minus infinity, you have to prove the existence of a number m such that whenever x is less than minus m, then the conditions of fx is always sandwiched within the epsilon sandwich as long as x is less than minus m. Okay, so in this case, here the case of m is played by the row of n here. So for all the x that is less than 1 over epsilon with a minus sign, then the functions is always sandwiched within this green region. So to summarize a little bit, so let me write it here. If you have a function that is known to have a limit of L when x tends towards positive infinity, you have to show that there exists a number of m such that whenever x is larger than m, it implies fx minus L less than epsilon for any epsilon that is positive. When you apply this to the case of fx equals to 1 over x, then L is equals to 0. So to this situation, in order to prove that L equals to 0 is the limit of the function when x tends towards positive infinity, you show that as long as the values of x lies in the region of m to infinity, meaning if you choose a values of m and if you allow x to only sitting on the right hand side of the values of m, then fx, which is 1 over x minus the limit of 0. Here L is 0, less than epsilon will always be fulfilled. Okay, so here the values of m is chosen to be 1 over epsilon. Whatever epsilon you put as a challenge, you just set m to be 1 over epsilon and then say this is the open intervals that would complete the proof that x equals to 0. X equals to 0 is the limit of this function when x is approaching infinity. Okay, so that finished up the discussions on the definition of the limit of fx when x tends towards infinity. Okay, so we have just shown that, and we also have shown that based on the figure 2.32. But the important thing here is not so much about the proof of the limit for 1 over x when x tends towards positive infinity using the definitions. What is more important here is to understand how to calculate the limit of a function as x tends towards plus or minus infinity. So I give you a function, say a function g and a function f, and I told you that the limit of the function exists when x tends toward plus minus infinity. The limit for fx is L when x tends toward plus minus infinity, and the limit of g when x tends toward plus minus is m. Then based on these two information, you are able to calculate the other limits that is expressed in terms of f and g when x tends towards positive infinity. So basically, theorem 8 is just a repetition of another theorem which we have mentioned earlier on in the previous chapter of, I think, 2.3. Right? In chapter 2.3, we also have a set of similar rules that allows you to calculate the limit of a function h, where h is comprised of f and g, either by adding the f and g, taking the difference between f and g, making the product of f and g, or taking the ratio of f and g, or raise the functions of f or g to another power. So that theorem that we mentioned in earlier chapters are those that applies for the limit when x tends towards an internal point. Here, for the case of limit at infinity, same set of rule also applies. So there's no difference between this set of rule and the set of rule that was mentioned in the topic 2.2, except here the limit is taken at infinity instead of taken at x0. So either the function's limit is evaluated at a fixed point of x0 or taken to infinity. As long as the limit exists, then the same rules would apply to a function of h which is comprised of another two known function which limits are known. So it's a very simple application of theorem 8. The important point of theorem 8 is that we are able to obtain the limit of a new function which is comprised of the other two functions which limits are known. Okay, so say for example, you know the limit of 1 over x when x tends toward plus minus infinity. You know they exist and this is 0. You also know that for a function of constants, the limit exists plus minus, and no matter what values of x is, the limit of a constant function is always the same as the value of the constant. So you know this limit, then you're asked what is the limit of the function of 1 over x plus 5. So this h is comprised of the sum of two functions So according to some rule, theorem 8, then the limit of h is just the sum of the limit of 5 and the limit of 1 over x when x tends towards positive infinity. So that is a very simple application of theorem addition rule number 1 in theorem 8. The other example would be example 5, where you have a rational functions that is made up of a constant divided by a polynomial of order 2. So here you can think of h as made up of f over g, where f is a constant and g is a polynomial of this. So the limit of h when x tends towards positive infinity is then just the limit of f divided by the limit of g for x tends towards positive infinity and for x tends towards positivity. So when I write down these statements, I am making use of the quotient rule. So once I have written down the quotient rule, then I just fill up what it is. Right? So the limit of the function of f here is a constant, and here is the limit of x going to positive infinity for g, which is x squared. X squared. Okay. So I think there is a little bit of not to say error, but I should not make use of the quotient rule here. If I make use of the quotient rule, then I still get an answer to be 0, but this would not be demonstrating the logics of applying the limit of this. So I should use another rule from theorem 8 instead of applying the quotient rule here. That's not to say that the quotient rule is wrong, but it would requires the knowledge of the limit of x squared when x goes to infinity. So this would of course give you a limit of 0, but it would requires you to make use of this statement that it goes to infinity. So which is not my intention to mention here, to mention this result here. So I'm going to answer this question by not using the quotient rule, but using another rules which is more appropriate, in the sense that I want to actually make use of the knowledge of these statements to solve my problem. 1 over x is equals to 0 when x goes to infinity. So let me try to redo example 7b again. So let me write it here. For example 7b, I am dealing with a function of pi square root of 3 divided by x squared, and x is tending to positive infinity. So to proceed with this, I first use the sort of like the product rule. Not the product rule, I think I'm going to use the constant multiply rule. Right? The constant multiply rules says if I have a function that is made up of a constant times n function, then I can always break it up into the constant, which is pi times 3 times the limit of the function, which is 1 over x squared. Right? So this should be easily understood. I just extract the constant out from the function 1 over x squared and write it into this form. Okay? From here to here, this is an application of the constant multiple rule. So now, in order to understand what is the limit of this function, I just have to look at what is the behaviors of this. So here I'm going to apply the product rule. The product rule says 1 over x squared is 1 over x times 1 over x. So 1 over x squared is the product of two same functions. So this should be then written as 1 over x times the limit of 1 over x for x going to positive infinity. So when I go from this line to this line, I break this into the product of two terms, and this is an application of the product rule where fx and gx in this case are the same function, which is 1 over x. So now I could make use of the previously known result, that the limit of this is known, right? We have already proven this in example 6, which is proven or exemplified in figure 2.32. So it's assumed that we already know this result. So we make use of this result that 1 over x has a limit of 0 when x tends towards 0. So this is 0. So you got a value of 0. So here we have just completed the proof that the limit of the example in 7b is just equals to 0. Okay, so this is also an example to exemplify the applications of theorem 8 onto a function that has a limit when x tends towards plus or minus infinity.